Well, hello, everybody. Good morning still the morning. Hope you're doing well, and you got some refreshments so that your speaking voices are clear. Should we need to randomly bring one of you up to do a 30-minute presentation? Just want to make sure. No, we're not? Okay. Hope you're enjoying the summit so far. This is the technical track here in this room. Next door, we have the business track. I'm sure you already know that by now, but I just wanted to remind you. Also, please make sure your phones are silenced. We do expect some more people to come into the room, so as I mentioned a few moments ago, if you are on the end of the aisle and you can scooch in a few seats, or if you happen to see someone looking for a seat, feel free to do that throughout the conference. That is very kind for the folks that are standing in the back when they come in. So this morning we had a lot of great stuff. We talked about the evolution of 5G Advanced. We discussed the role of AI in 5G. We also took a deep dive into RF modems. So we learned a lot, and we're going to keep that going. Now, just in case you might be in the wrong room, next door, they're going to be talking about marketing 5G user experiences in a diversified world. That's going to be happening moments from now. But here, I assume you're all in the right place. We're going to be talking about 5G mmWave myths versus reality. We've got a very special guest. He's the president of the Signals Research Group. Please welcome to the stage, Michael Thelander.
Great, so I'm already 29 minutes left in my presentation, so we'll go ahead and kick right off here. So what I'd like to do today is really take you around the world to look at 5G mmWave performance. We'll start off in Helsinki looking at Elisa's network deployed there. We'll then return back to the United States. You heard yesterday Verizon Wireless talking about what they're doing with the Phoenix Suns. Well, this is a study we did at, basically at the Footprint Center where the Phoenix Suns play basketball. Actually, the day before I was there, the Eagles had 2 nights of concerts, and after I left, it was Disney on Ice. So clearly there's a lot going on at the Footprint Center besides NBA basketball. And then lastly, I was in Tokyo, Japan, right after Easter back in April. We'll take a look at what the operators are doing there with respect to mmWave. So now let's go to Helsinki. I was actually here in late September of last year. And the idea here is to really look at how is the operator using mmWave there, keeping in mind they have LTE. They also have 100 megahertz of 5G deployed in their midband spectrum. So this is a test we did in downtown Helsinki. And it's really designed to look at the coverage and the capacity that you get with LTE, comparing that with midband 5G, and then lastly, looking at what do you get when it comes to mmWave. So again, this is testing in downtown Helsinki. It's in a central plaza, really in the heart of the downtown, and it really involved 3 separate walk tests within one cell sector or one cell PCI, looking at LTE performance, repeating the test, looking at midband performance, and then lastly, looking at mmWave performance. And so what we've plotted here is really, you see the different colors. We'll start off on the LTE side, on the left-hand side. You see the different colors there. What you want to focus on is really the white color. That is the sector of interest for LTE. We have identical plots that would show it for the other 2 bands. The operator has deployed in LTE, but they don't fit on this slide. And then in the middle there, that's the midband 5G. And the first interesting thing that you will note is that the coverage, if you look at kind of that purplish color there, it's very similar to LTE. In fact, I would argue it's almost identical, especially from an outside perspective. And I think that's kind of interesting, just given the differences in the frequency bands. But again, this is a densely populated area or a dense cell site location here. So clearly, the operator is not deploying their LTE for basic coverage purposes. And then lastly, we have mmWave on the right-hand side. And again, if you look at kind of that magenta purple or a pinkish color there, you see the coverage with the mmWave is pretty similar, or there's at least a lot of coverage compared to what you get with both LTE and midband. The other interesting thing to look at, and it's a little bit hard to see in this figure here, but if you look along the right-hand side there, you can see that we had coverage with mmWave basically along that entire street. You compare that to band N78, and we actually handed off to a different cell site. So yes, there was midband coverage there, but it was coming from a different radio. The other point to make is that, and you can't see it here, but you see that little yellow marker there. That's the site of the N78 N78 and the mmWave radio. That's actually non-line of sight going to where I was walking along that street there. And I knew that because I was walking next to the building, and the building's 2 or 3 stories high. So the only way that signal could get to me where I was at there was bouncing off that building on the other side of the street. I think that's kind of interesting. So now let's go on and look at the results. So first of all, let's start off with LTE. And so kind of our methodology here again is we're doing a walk test. We're doing a full buffer data download. We're collecting all of the signer information there you see on the left-hand side, basically the signal quality that you're seeing in the LTE network. We did it across all 3 bands. And then we geo-bin the data to make sure that we're not kind of weighting things based upon being in a really good signal quality area versus a very poor signal quality area. So when we do that, we're able to map that to what the expected or what the actual throughput was based upon more extensive testing that we did across Helsinki. And then we also use what I call resource block normalization. So basically taking the physical layer throughput that you observed and then scaling it up to adjust for all of the resource blocks being assigned to your phone. Because again, it's a commercial network. There's other users out there. You want to make sure you capture the full capacity of the network. So when you do that, you see basically the total sector throughput for each frequency band. You do simple math, and you can equate that to basically the spectral efficiency by taking your average throughput, dividing it by the channel bandwidth. And so on the right-hand side there, that's your spectral efficiency that you get for the 3 LTE bands that were deployed in the network there. So now let's turn to midband 5G. Again, very similar. On the left-hand side, you see basically where I walked. You see the SINAR, or the signal quality, that was available at those locations. In this case, I'm actually showing the distribution of the SINAR, so a little bit different because I only had 1 band to work with. You see the average SINAR there, and again, taking data that we collected across all of Helsinki doing walk testing to get really more representative data. You see what the expected average throughput is across that entire sector based upon the signal quality that we observed. And again, that's 841 megabits per second expected average throughput across that entire radio. Now let's go to 5G, or 5G mmWave. And again, very similar methodology, basically turned off mid-band on the 5G radio, so everything is being forced to mmWave. You see the average SINAR, the signal quality distribution there. If you start doing the math and you look at what the expected throughput is for that given SINAR value, you get basically 1.7, 1.8 gigabits per second. We did a second test, and we actually got much better results. The problem there is we lack some of the geo-binning data that was available, and so I wasn't comfortable using that data. So basically, the way I would look at it is that the results we're showing today actually understate the full performance of mmWave. So what does this all mean? So now we start doing some, uncomplicated math to really look at what is the capacity and the coverage that you get with each technology. Now, on the left-hand side, you kind of see that capacity cake. And this is a cake that you've seen, going back to the days of 2G, 3G. And back in those days, the lowest layer was 2G. Kind of that middle layer there was edge. And then on top of that, that was UMTS at 2.1 gigahertz. And the reason they did that is because nobody thought you would deploy 2.1 gigahertz across an entire nation. Interestingly enough, when I tested in Elisa's network, they were using band 7, which is actually a higher frequency band, around 2.5 gigahertz, as the anchor band for 5G. So what does this mean? So first of all, you look at the lower layer there. The coverage, this is drawn to scale. The coverage you get with LTE is relatively modest. Now you throw on that mid-band capacity layer, and you basically double the total amount of capacity available in that sector. And basically, I'm assuming it's very close to a one-for-one coverage area. Now, you go back and you think about what the various vendors forecast for mobile data growth. And they're all talking about data growth continuously increasing. If they were to say, well, I think data growth on mobile networks is going to roughly double, and then it's going to decline. Well, if that's the case, well, then mid-band 5G is all you need, because you basically get a 2.3x increase in capacity. But that's not the case. You actually need more capacity on top of that. And that's where mmWave comes in, really providing that additional capacity once you've saturated all of the available capacity that you get on your midband network. So kind of doing the math there, and this is being shown on the right-hand side here. Essentially, you get, again, about a 2.1x increase in capacity, or 2.3x increase in capacity with midband compared to LTE. Now you factor in the 5G mmWave, it's a 10x increase on top of LTE, and it's basically a 4.4x increase in capacity on top of midband. So I guess I would argue that when you think about mmWave, it's not so much providing one user with a very high data speed. It's really about serving lots of users, getting them the throughput that they need, especially as networks become more loaded over the coming years. So now we're going to switch gears, return back to the US in Phoenix, Arizona, home of the Phoenix Suns at the Footprint Center. So this is separate testing that we did there, and this was kind of testing in an area where they had their refreshment stand set up. Nice area to test. This is where everybody comes to buy a beer during halftime, or if their daughter is watching Disney on Ice, they try to get away and get a much-needed drink. And so we had, in this case, we had 16 phones. And the idea is to really load up the LTE network, see what kind of capacity we get, and then kind of basically turn on mmWave. So we did a lot of tests, and I'm going to highlight some of those tests today. So this is one test. Again, we had 16 phones. We had 12 of those phones on LTE. What we're showing there on the left-hand side there is kind of the total throughput that you get on each LTE band that Verizon had in that venue. And you see basically the total throughput that is shown there. And then on the right-hand side, the blue, that is each mobile device's physical layer throughput. Again, there was 3 carrier aggregation. So most of those phones, you see they're getting 20 to 30 megabits per second. That's not on one LTE band. That's 3 LTE bands with carrier aggregation. Now let's look at the 5G results. So we had 4 phones where we enabled them with 5G mmWave. You see substantially higher throughput. It's around 3.3 gigabits per second spread across 2 5G mmWave radios that were also slightly covering that same area. So what that tells you is, first of all, 5G mmWave offers substantial capacity. On top of that, by moving those phones onto 5G mmWave, the capacity or the throughput available to those remaining LTE phones also increases, because you basically shifted your traffic from LTE to mmWave. Now let's look at the uplink. So again, this is a very similar methodology, but in this case, we've turned on mmWave on 4 phones. Now in this venue, Verizon did support PDCP combining in both the downlink and the uplink, basically allowing you to aggregate LTE and 5G bandwidth to the same phone. We didn't observe it necessarily in the downlink. We did see it in the uplink direction there. So you see 4 of the phones, they're getting both LTE in the uplink direction as well as 5G mmWave in the uplink. I'd also point out the phone in the middle there, mobile device number 9, that was also supporting 2 carriers of uplink on mmWave. That explains why its 5G mmWave throughput is much higher. So again, the idea here is that if you have 5G mmWave enabled on your phone, your available capacity in the uplink, or your total data speed, on average, was about 3.7 times higher than what it was on a phone that's only operating in LTE. So the question now becomes, why do I care about data speeds? I don't need those kind of data speeds. But again, it's not the peak data speeds. It's really about the capacity that mmWave offers. So this is testing we did also at Phoenix, but looking at it from the user application perspective. And this is video. So the idea here is that we're actually using YouTube Live. We're broadcasting a video up to YouTube Live where people can watch it live, just like me speaking today. So in this case, we had a 5G phone serving as a hotspot connected to the PC, and then it's basically using 5G mmWave as the backhaul going out to the internet. So the left-hand side is an unloaded network. This is the physical layer throughput that is required to support YouTube Live in the uplink direction. And you see it's right around 11 megabits per second fairly consistently. There's one little blip there. I think that was some sort of buffering taking place in the phone during the test. But bottom line, it's very consistent. Now in the right-hand figure, we basically took those other phones there. We turned on LTE. They picked their band. It was theirs to choose. And you see what happens. So you see the blue line there. That is what happens to that phone that we had doing YouTube Live in the uplink. All of a sudden, its performance is much more erratic. Now, in this case, we actually got very lucky. It turned out that the video performance was fine. But every time you can kind of assume if your physical layer data speed in the uplink drops below 11 megabits per second, especially for a sustained period of time, that is when you start to see buffering. You start to get a very poor user experience. And we'll show that in a slide or two. So that previous slide, that was all LTE. Now let's turn on 5G. So in this case, again, we had our 16 phones doing something on LTE or 5G. We had a 17th phone that was doing this YouTube Live broadcast. In this case, we actually locked the phones to band 66. And again, there were two different bands the operator had in the venue supporting band 66. So we had those 14 phones on LTE. That's accounting for the 39.4 and the 32.8 megabits per second kind of allocated between those 14 phones. And you kind of do the math in your head and you realize there's no way in heck any of those phones could give you a good user experience with YouTube Live because they're nowhere close to getting 11 megabits per second on an individual phone. That's the total throughput for all 14 phones. Now you look at it from a 5G mmWave perspective. So in this case, we had two phones doing full buffer uplink on mmWave. On top of that, we had the third phone doing the YouTube Live video broadcast. And what you see here is that there's actually ample bandwidth available for that YouTube Live broadcast. In addition to that, we have the full buffer data traffic going on in the background. So here's why it matters. This is actually the video experience. This is real data that we collected using YouTube Live. So on the top, this is a video that we were streaming live to YouTube Live. On the left-hand side, that's the source video. So that's what you would see if you've played the video on your phone. You see its video quality score or its video MOS score is quite good. Now you shift to the middle image here, and this is basically the same time capture, essentially the same frame. You see a lot of pixelation. You really can't make out what's going on there. Definitely a degraded experience there. And then lastly, on the left-hand side there, that is that same video, but now instead of streaming it over the congested LTE network, we're doing it on 5G mmWave. And you can see, just comparing the far left to the far right, the video image is basically the same. That's much different than you would get with the congested LTE network. And then on the bottom there, it's just a similar test we did. You see the markers there. That's basically a specialized video that allows you to look at the frame rate, look at video impairments, et cetera. You see on the right-hand side there, the bad image. You see two of those circles there, the one on the far left, the one on the far right. You see a lot of impairments there. That's the experience you get, even with only 11 megabits per second when you're on a congested network. So now we're going to switch gears one more time and go to Tokyo, Japan. And again, I was there 3 weeks ago, and you heard yesterday talking about 4 mobile operators have deployed millimeter wave there, I'd like to showcase just some of the results that we captured there. So this is an uplink test that we did just outside of Tokyo Station. It's where everybody takes a train into Tokyo or out of Tokyo. I took it on my way back to Narita. This is a walk test, and what we're plotting here is essentially the physical layer uplink throughput during this walk test. Now, if you can see the image, I've actually identified 2 areas where the phone handed down to mid-band 5G. So clearly, you don't have coverage everywhere. At some point, you fall down to mid-band 5G. One thing to point, though, if you can see that figure, especially on the right-hand side of where it says mid-band 5G, as I walked out of millimeter wave and I started coming back in, it took a while for the phone to switch back to millimeter wave. So somewhat, we've understated the true performance of millimeter wave in the right-hand bar chart there, because there was a period of time there where millimeter wave was clearly available, but because I was doing an active data session, the phone remained on mid-band 5G longer than it probably should have or could have. Now let's look at the results. And again, this is a network where the operators have 400 megahertz of spectrum available. The Japanese operators are also much more aggressive in taking advantage of uplink on the 5G millimeter wave. Most of them have 2 carriers being used in the uplink direction, basically giving you 200 megahertz of available capacity. And that's probably the one thing that impressed me the most about Japan, is that all the cell sites supported it, and the availability of tapping into that was pretty substantial. So let's look at the results here. So a separate walk test, not shown. I had the phone locked to mid-band 5G the entire time. You see on the right-hand side there kind of the throughput that was available, 52.2 megabits per second on average, spread across both LTE and 5G. The middle bar there, that's what you see shown there on the left-hand side. So that is a mix of the phone being in 5G mid-band as well as 5G millimeter wave, depending on where I was in the walk test. And then lastly, if you wanted to ignore the mid-band 5G portion of that walk test, that's the information you see on the left-hand bar chart there. And so the point here is that if you're comparing just the mid-band 5G versus 5G millimeter wave, it's anywhere from a 3x to a 4x increase in available capacity from millimeter wave compared to 5G mid-band. This is a picture taken during this walk test. If you look real closely there, you can probably see the 5G millimeter wave radio. I was 160 meters away based upon Google Earth. From that location where I took that picture, I had 2 gigabits of sustained throughput in the downlink. I had 300 megabits of sustained throughput in the uplink. That's substantial, again, with only 400 megahertz of spectrum available. You think back to when Verizon first launched 5G millimeter wave, you might have seen around 1.2 gigabits per second kind of sustained. You might see peaks a little bit higher. But clearly, if you look at the downlink throughput, it's improved substantially from then versus now. And again, that 2 gigabits per second, that was at a quite a good distance away. You think about what it took to get to 1.2 gigabits per second back in April 2019. You had to stand under the cell site to get that. So clearly, there's been a huge improvement in the robustness as well as the overall spectral efficiency of 5G. And then when it comes to the uplink, when Verizon first launched millimeter wave back in April 2019, everything was going over LTE. You look at it today, it's not only 1 carrier in the uplink, it's 2 carriers in the uplink. You're getting 300 megabits per second of basically sustained throughput at a lot of locations. This is actually going to 4 carriers in the uplink, hopefully sometime later this year, depending on the operator. Separate test, again, this is looking at the uplink direction. This is somewhat close to my hotel. The idea here is that I knew there were several sites that had 5G millimeter wave, basically going around capturing at individual data points what is my performance in the uplink direction. Did one test where I disabled millimeter wave on the phone. In the second test, I enabled millimeter wave. But I also tried to test until I walked or moved outside of millimeter wave coverage. So on the right-hand plot here, on the right-hand geoplot, I've highlighted some areas where the phone actually was on FR1, midband 5G, and not millimeter wave. On the left-hand image there, that's where the phone was locked to band N78 the entire time. So now if you look at the results again, keep in mind there is an LTE component as well. But if you look at just comparing FR1 to FR2, the midband or the millimeter wave performance is about 2.4x higher than it is over midband 5G. And then down below, just another way to look at the data. This is more so from a user's perspective, that if you factor in both the LTE component as well as the one carrier of 5G that you'd be getting over midband 5G, or the two carriers that you get with 5G millimeter wave, there's basically a 1.7x to a 1.9x increase in the user data speeds based upon these data points that we collected. I threw this slide in kind of late in the day based upon some discussions that occurred during some of the analyst and media briefings, concerns about energy efficiency and do I want millimeter wave on my phone because it kills the battery? And I would say the following. So first of all, definitely 5G millimeter wave has an impact on the battery. But you have to put things into context. So first of all, if your backlight is turned on, your backlight can be several hundred milliamps of current drain just having your backlight on. So, and the other thing to think about too is that if you're doing a data transaction over millimeter wave, it happens far more quickly. So yes, you're draining, your battery is being impacted, but conversely, you're also transferring a lot more data. So let me give you an example here before I start talking about these data points here. I was at my son's lacrosse game the other night before I came here, and he was excited. He scored a goal. He wanted me to send him some video. So I had taken several video clips during the game, and each video clip was about 20 megabytes or 20 megabytes of data. So it was too big to email. I could have texted it, but that would compress it. So I figured I'll just upload it to Google Drive, send him the link, he can download it, we're all fine and happy. So I had my phone, and the phone said I was on 5G. I won't say the operator, but it was band N5. I assume it was 5G, it might have been LTE as well. I swear it took easily 5 minutes, perhaps 10 minutes. I kept looking at my phone, watching the dial spin. I thought I had timed out. So yes, maybe my current consumption based upon that LTE transaction was relatively low. It was taking 10 minutes to do that transaction, plus my backlight was on. Now you imagine doing that over 5G millimeter wave where you have a very fast uplink connection. During those few seconds that it took to upload, yeah, maybe your energy consumption was very high, but then it stopped, and then you turn off your phone, or at least you turn off the backlight. You can't do that when you're watching your phone for 10 minutes, hoping that video gets uploaded. So now let me explain the data here. So this is actually relatively old data. This is with the Galaxy S10, which is definitely a legacy 5G millimeter wave phone. This is testing that we did back in Minneapolis, where Verizon's had deployed millimeter wave. Again, this is probably 2020, I believe. And this is looking at what is the total amount of data that I can download to my phone under various scenarios. So we've broken it down into 3 different categories. Again, this is taking into consideration, is my backlight on? Is my backlight at full brightness? Is it at 50%? Because that definitely drains a lot of current. So what it turns out is that in this case, 5G is far more energy efficient than it is over various combinations of LTE involving 2 carriers, 3 carriers, et cetera. To give you a little bit more background here, on the far left-hand side there, where I say it's basically excellent 5G millimeter wave performance, that was an application layer throughput of only 750 megabits per second. So that's not screaming speeds on 5G millimeter wave today, but it's pretty good. And then from the LTE side of the house, looking at the various results there, is anywhere from 75 megabits to about 150 megabits per second of sustained throughput at the application layer. So again, it's good speeds, it's not great speeds, but the point here is that you really need to think about things in context and what you're doing with your phone and the other things that come into play that really impact your battery. I would also say that this is probably a best case scenario, to be fair. If you think about using 5G millimeter wave to do a Skype video chat, that's probably not something you want to have happen. I mean, because quite clearly, you'd be having an impact on your battery much more so than LTE. So everything kind of needs to be balanced out and thought about. But at least in this case, this is clearly an example that would show you that energy efficiency, depending on what you're doing, can be substantially better on millimeter wave over mid-band 5G or LTE. So just to wrap things up here a bit, first of all, keep in mind, millimeter wave is no longer a US-centric technology. We've been to Europe, we've been to Asia. It exists, I've been there. You also need to think about, do I really care about peak speeds, or is it really about total data capacity? And again, I would argue, both from a downlink as well as an uplink perspective, it's really about the total capacity that 5G gives you, millimeter wave, versus anything else. It's also no longer a downlink technology. We've got 2 carriers in the uplink today, going to 4 carriers in the uplink sometime later this year. And then lastly, energy efficiency. Again, put things into context. Think about what you're doing on the phone and the other thing that that phone could be doing in terms of the backlight, et cetera. We've published several papers on behalf of Qualcomm over the years. This is a paper that basically provides the results from the Helsinki study as well as the study we did with Verizon. If you're interested more about the energy efficiency, this was a paper we did last year. I forgot the name of the report. And then lastly, we do have plans to come out with a paper in the next few weeks that really looks at, in more detail, the results from our testing in Tokyo. And a special thanks out to Spirent and AccuVer Americas for their test equipment. They've been valuable partners for the last several years, and without them, we couldn't be doing these studies. So with that, I thank you very much.